The first part of Chapter 13 studies sequences and series. A sequence is defined as an ordered list of numbers. A recursive sequence is when subsequent terms depend on a previous term or terms, and then a series is when you add the terms of the sequence. The first example that we'll look at has the sequence defined as the nth term is term number minus 1 divided by term number plus 1. This is the formula that you plug into, and to find the term, you just take the number and substitute it in for n. So the first term is 1 minus 1 over 1 plus 1, which equals 0. The second term is calculated by saying a2 equals 2 minus 1 over 2 plus 1, which produces 1/3. The third term, plugging in a 3 minus 1 over 3 plus 1, which is 2/4, reduces down to a half. The fourth term, 4 minus 1 over 4 plus 1, 3/5. And then the fifth term, 5 minus 1 over 5 plus 1, which is 4/6 or 2/3. Sometimes sequences can be plotted. The term number goes along the x-axis, and then the result, or the term, goes along the y-axis. So for term 1, we get 0. For term 2, we get 1/3, 0.3 repeating. Term 3 is a half. Term 4 is 3/5, which is 0.6. And term 5 is 2/3, which is 0.67. So it appears that as the term number increases, the pattern is going to slowly flatten out. Second example will also be graphed. This time the sequence is defined as 1 over n squared. So the first term is 1 over 1 squared, which is 1. The second term, 1 over 2 squared, which is a fourth. The third term, 1 over 3 squared, which is a ninth. The fourth term, 1 over 4 squared, which is a 16th. And then the fifth term, 1 over 5 squared, which is 1/25. And again, if we plot these, 1, 1, 2 1/4, 3 1/9, 4 1/16, and 5 1/25, produces a sequence that looks like it's decreasing down to closer and closer and closer to 0. The third and fourth examples are more famous sequences. The third example uses as its name a capital F, and that's because this is an example of a Fibonacci sequence. This means the first term is 1. This means that the second term is also 1. And this means that each subsequent term is based on the previous term and the term 2 steps back. So the table's been started for us. The first term we were told was 1, and the second term we were told was 1, so there's no calculations for us. The third term is defined as the second term plus the first term, and if I look up here, that's 1 plus 1, which is 2. The fourth term is the third term plus the second term, so that's 2 plus 1, this plus this, for a total of 3. And now when we need to start to calculate, the fifth term is going to be defined as the fourth term in the Fibonacci plus the third term, which is 3 plus 2, equaling 5. The sixth term is defined as the fifth plus the fourth, and that's going to equal 5 plus 3, or 8. The seventh term is defined as the sixth plus the fifth, which is 8 plus 5. And then the eighth term is the seventh plus the sixth, which is 13 plus 8, or 21. So the first 8 terms of a Fibonacci sequence are 1, 1, 2, 3, 5, 8, 13, and 21. Similar example is not a famous sequence, but the first term is given as 1, the second term is given as 2, and then subsequent terms are defined as the ratio of 1 step back divided by 2 steps back. So again, the first and the second terms are given to us. The third term is the second divided by the first, which is 2 divided by 1, which is 2. The fourth term is defined as the third divided by the second, which is 2 divided by 2, producing 1. The fifth term is the fourth divided by the third, which is going to produce 1 divided by 2. The sixth term is equal to the fifth divided by the fourth, which is 1/2 divided by 1, which is 1/2. The seventh term is defined as the sixth divided by the fifth, which is 1/2 divided by 1/2, which is 1. And then the eighth term is defined as the seventh divided by the sixth, which is 1 divided by 1/2, which winds up equaling 2. So in this sequence, we have kind of a strange bouncing back and forth between fractions and whole numbers. This pattern goes 1, 2, 2, 1, 1/2, 1/2, 1, 2. I don't know if it repeats, and we don't need to graph it. It's just an interesting sequence. This is a famous joke that involves sequences in series, and it also involves an arithmetic sequence, which we'll learn about in the next section. The fifth and sixth examples start like this. Again, we have the first term given to us, and the formula for the nth term is fairly intimidating, but the process is just double the previous term and add 2, and then divide by the opposite of the previous term. So if I know the first term is 1, to find the second term, I'm just going to take the first term and plug it in here and here. Well, the first term I was told is 1, so 2 times 1 is 1, 2 times 1 is 2, plus 2 is 4, divided by -1 is -4. The third term is twice the previous one, so that's 2b2, plus 2, all divided by the opposite of b2. So I need to look up the second term, which was -4. 2 times -4 plus 2 over the opposite of -4. So being careful, I get -8 plus 2 is -6. And the opposite of a -4 is a +4. So I get a -3/2. This green box is here because I want you to calculate the fourth term on your own. You're going to be asked to submit that on the web page. But as a hint, if you do the fourth term correctly and then get the fifth term calculated, you should get a 1. The sixth example gives us b sub n equals -2, and this time we want to find a series. This column asks you to find each term, so the sequence will be the boxes that get filled in this column, and then s sub n represents the sum, and that's what we call a series instead of a sequence. So the first term, I'm going to plug 1 into my formula and get 2 to the -1, which is 1/2, and the sum of the first one term is 1/2. The second term, I'm going to plug 2 into my formula and get 1/4, and then the sum of the first two terms, s sub 2, is 1/4, so 1/2 plus 1/4, which is 3/4. The third term, plugging 3 into our formula up here, 2 to the -3 is 1/8, because 2 cubed is 8. And then the third term in the series is 1/8 plus 1/4 plus 1/2. So now I'm going to take my previous answer of 1/2 plus 1/4 and add on 1/8. And that total winds up equaling 7/8. The fourth term is 2 to the -4, which is 1 over 2 to the 4th, or 1/16. And the sum of the first four terms is going to equal 7/8 plus 1/16. So if I take the previous sum and add 1/16, I'm going to wind up with 15/16. And then finally, the fifth term in the sequence is 2 to the -5th, which is 1 over 32. The fifth term in the series is the sum of the first 4 plus 1/32, so I've got 15/16 plus 1/32, which winds up equaling 31/32. So that's our first example of both a sequence and a series side by side. Seventh and eighth examples continue on asking us to find a series. This time, however, the formula is defined a little bit differently. I have the n plus 1 term is defined as the nth term times the previous two terms. And the n plus 1 term just means that we're shifting where the index is. I still have what's called the first term equaling 1, the second term equaling 2, and I need to fill in the rest of the sequence and also keep track of the series at the same time. So when I plug n equals 0 into my formula, I wind up with a sub 1, which is 1. I was given that. When I plug 1 into the formula, I'm looking for a sub 2, which I was also given as 2. To find a sub 3, I need to use a2 times a1, which is 2 times 1, or 2. To find a4, that's going to be the third term times the second term, which is going to be 2 times 2, and I get 4. So if I go back and start to fill in the series, S1 is going to equal n is 0. So when I plug in 0 down here, I get S sub 1. That's the sum of the first term, 1. S2 is going to be the sum of the second term plus the first term. 2 plus 1 equals 3. S3 is going to equal 2 plus 2 plus 1, which is 5. S4, as you could probably figure out on your own, is going to be sum of the first 4 that I see over on the left column. So 4 plus 2 is 6, plus 2 is 8, plus 1 is 9. Finding the fifth term, A4 times A3, which is 4 times 2, or 8. The sum of the first 5 is 8 plus the previous 4, or 17. And now the last two you're going to find on your own, and your S sub 6 is going to be a question that you need to answer on the web page. The last two examples are going to involve sigma notation. A giant capital sigma just means summation. So this statement right here is saying sum all of the answers that you get when you start by substituting 2 in for k and stopping when you reach 6, incrementing k by 1 unit each time. So what this really means is plug 2 into this formula, get an answer. Plug 3 into the formula, get an answer. Same thing for 4, 5, and 6. Take all those answers and sum them together. So if we take 2 and plug it in this formula up here, we get 1 minus 2 times 2. 1 minus 4 is a negative 3. If I take 3 and plug it into the formula, I wind up with 1 minus 2 times 3, which is negative 5. Plug 4 into the formula, I'm asked for 1 minus 2 times 4, which is negative 7. I'm asked to plug in 5. 1 minus 2 times 5, which is negative 9. And I think we can see the pattern, negative 3, negative 5, negative 7, negative 9. And then plugging 6 into the formula, 1 minus 2 times 6 is negative 11. So to answer the final question, the sigma means take and add all those answers together. So the sum of this quantity, when k is substituted from 2 up to 6, incrementing by 1 each time, is the sum of negative 3, negative 5, negative 7, negative 9, and negative 11, which happens to be negative 35. So the answer to this is negative 3 plus negative 5 plus ... And when I get all done adding those up, I wind up with negative 35. And then the final two examples continue with the sigma notation. One we're expected to substitute to find the sum of a bunch of terms, and then a backwards problem where we're giving you a sequence and you have to find the formula using sigma notation. The difference in the seventh example is that there are two variables. There's an n sitting here and an x sitting here. The index down here tells you that you're going to substitute in for n. So when n is 1, and when I plug in up here, I get 1 minus 1 times x raised to the 1 minus 2. 1 minus 1 is 0. 0 times anything is going to be 0. So even though x to the 1 minus 2 is x to the negative 1, or the reciprocal of x, the 1 minus 1, which is 0, multiplies that and produces a 0 answer. The second term, I'm going to plug 2 in, but only for n. So I'm going to have 2 minus 1 times x to the 2 minus 2. I had to substitute in here for n and here for n. So that winds up equaling 1 times x to the 0. Well, 1 times x to the 0 is 1 times 1, which is 1. And in the third term, 3 minus 1, x to the 3 minus 2. And so that winds up equaling 2 as the coefficient and x to the first, 2x to the first. Well, since the question asked you to sum all three of those terms, substitute 1, substitute 2, substitute 3, and add them together, I look down this column and find out that I have 0 plus 1 plus 2x, or a sum of 1 plus 2x. So it is possible to have a summation question with two variables. You just need to pay attention to what the index is and where to plug in. And then the last example, like I said, goes backwards. I'm giving you a sequence and you have to come up with the formula for that sequence. Well, the first thing I notice is that all numerators are 1. So that's going to be pretty easy to put into a formula. The second thing I notice is that the denominator keeps changing. And if I look for a pattern, this is 2 to the first, this is 2 squared, this is 2 cubed, this is 2 to the fourth, this is 2 to the fifth, 2 to the sixth, and 2 to the seventh. So each of these numbers have a base of 2. And if I count term numbers, it looks like this is the first term, second term, third term, fourth term, fifth term, sixth term, and seventh term. So I think the key to this formula is realizing that the denominator is 2 raised to the power of the term number. So I think I'm ready to start building my formula here. I'm going to have summation. I'm going to have a 1 in the top always. I'm going to have a 2 in the bottom, but 2 is going to be raised to some power, and I can use any counting variable that I want. Most people choose n. I'm going to choose n equals 1 all the way up to 7. If I put an n up here, I will have, when I substitute 1 over 2, which is what I have up here. If I increase my n to 2, I'm going to have 1 over 2 squared, which is what I have in the second term. And if I continue that pattern all the way up to the seventh term, 1 over 2 to the seventh is the last term. The final piece to figure out is the sign. It seems to alternate back and forth between negative and positive, negative and positive. So if I'm thinking, well, if I take negative 1 and raise it to the term number, negative 1 to the first is negative, negative 1 squared is positive, negative 1 cubed is negative. That seems to be backwards from what I want. I want the first term to be positive, the second term to be negative. So that formula isn't going to work. If I try something along the lines of negative 1 to the n plus 1, I take all odd numbers and change them into even when I bump them up by one more unit. So negative 1 raised to the 1 plus 1, or negative 1 to the second, becomes positive. Negative 1 raised to the 2 plus 1 is negative 1 to the third, which is a negative. Negative 1 to the 3 plus 1 is negative 1 to the fourth. A positive exponent turns all negatives into positives, and I think that's what I need. So to get a positive, negative, positive pattern, I need to take my numerator, change it to a negative 1, and raise it to some power that increases the exponent or changes it from even to odd. There's different ways of getting the sign to alternate from negative to positive, so it didn't necessarily have to be in this form, but this form at least works. So that's my final answer. I've converted a sequence into something with sigma notation. So that's it. 8 quick examples, 10 quick examples on how to do sequences in series, and then the next section will involve how to do sequences in series for arithmetic.